This is a flow network. You have a source node where flow is emanating from and a sink node where the flow will reach. Nodes are joined with weighted directed edges where each edge weight defines the maximum flow which can be sent through this edge, also known as its capacity. Typically in flow networks, the challenge is defined: if we push flow through these edges, what is the maximum flow that can reach the sink? In this video, we will first cover useful flow network properties. Then we will do a walkthrough of the Ford-Fulkerson method for finding the max flow. We will then do a larger example. Finally, we will code this with the Edmonds-Karp implementation in C++. Flow networks have a source node where flow is coming from and a sink node where flow will terminate. Each edge weight defines the capacity of that edge, i.e. the maximum amount of flow which can be sent through that edge. Let's look at the paths in this network. Imagine these are pipes or something similar. Our first constraint is all edges in the graph can only carry a flow which is less than or equal to its capacity. For example, if this edge is a pipe and it has a capacity of 5 liters of water per second, you cannot push through, say, 6 liters of water per second or it will burst. So in the top path, we could push 5 units of flow through the first edge, but then the second edge only has a capacity of 3, so only 3 units of flow can possibly be carried through that edge. This means that the total amount of flow which can reach the sink from this top path is actually reduced to 3. Edges which cap the flow of a path in this way are called bottlenecks. The bottleneck is the edge which can carry the least amount of flow in a particular path because it restricts the flow of the entire path. So let's update the first edge in this path to be 3, because our second property is, for all nodes other than the source and sink, the flow into the node must equal the flow out. In the bottom path, we can push 2 units of flow through the first edge. Even though the second edge has a capacity of 4, only 2 units of flow entered it from the first edge, so it will simply transport these 2 units of flow to the sink. In the bottom path, the edge with the weight 2 is the bottleneck, being the edge with the smallest capacity in the path. Under these constraints, the network flow is the sum of the flow values on the edges which enter the sink, or the sum of the flow values on the edges that leave the source. In this case, that's 3 plus 2, which is 5. In this example, 5 is also the max flow, which can reach the sink. It begs the question, how do we find this max flow programmatically? You might think, based on the previous example, we could just keep finding paths from S to T, then we find the bottleneck of the path, and push the most flow we can through each path capped by the bottlenecks, then return the final network flow as the maximum flow. For example, in this case you might think, the bottlenecks of the top and bottom paths are 3 and 2 respectively, so let's push 3 and 2 units of flow through these paths to get the max flow value of 5. But let me show you an example where this approach fails. Here is the path, the bottleneck is 1. Let's push 1 unit of flow through this path. Now let's look for another path. Here's one. The bottleneck capacity is 1 because the second edge only has room for 1 more unit of flow to be pushed through it. So let's push 1 unit of flow through this path. Now there are no more paths left from S to T, so the maximum flow is returned as the sum of the flows leaving the source, or the sum of the flows entering the sink, 2 in this case. But this is the wrong answer. If we consider these two paths, we can see the maximum flow is actually 3. So the greedy algorithm fails because it depends on the order of paths you choose. Ford-Fulkerson addresses this problem by making one tweak. After we push the flow through a path, we then insert a back edge for each edge in the path, and we set the capacity of this new back edge to be the flow we push through that edge. This means we have the chance to correct our flow if we saturate an edge and leave ourselves with no paths left, because we all make mistakes. Let's walk through the algorithm. Initialize the flow on all edges to 0, then while there is a path P from source to sink in the network, find the bottleneck capacity of the path. In this case, the bottleneck is 1. Send a flow equal to the bottleneck through all edges in the path. We push 1 unit of flow through all these edges. And now here's the extra step. For each edge in the path, draw a back edge whose capacity is the flow sent through that edge. In other words, the capacity of these backward edges will all be 1. So this gives you a chance to backtrack the flow on this edge in future iterations. Think of these back edges as giving you the ability to take away flow from this path and move it to another path. When we push flow through a back edge, we actually deduct that amount of flow from the corresponding forward edge. Let's keep looking for paths until we run out. Here is another one. The bottleneck capacity is 1 because the second edge can only carry 1 more unit of flow before it's at capacity. So push 1 unit of flow through this path. Note that the flow through the second edge is 2 now, so we need to update the capacity of the back edge to 2. This is because we can correct up to 2 units of flow now. And draw the back edge for that first edge in the path with a capacity of 1 since the flow is 1 through that edge. There is one more path here. Can you see it? Yes, we can now take the back edge. We can push 1 unit of flow through this path. Note that when we push 1 unit of flow through the back edge, we minus 1 unit of flow on the forward edge because we are correcting our previous flow push through that edge. Now backtrack and update the back edge capacities to match the new flows. Now there are no more paths from S to T, so the final flow is our maximum flow. The final flow being the sum of the flow values on the edges leaving the source, or the sum of the flow values on the edges entering the sink. The important thing to remember is that for all nodes other than the source and sink, the flow into a node equals the flow out. You can look at the final graph and confirm that that is true. Let's do the example that we saw at the very beginning. Firstly, look for a path from S to T. This looks like a good one. Find the bottleneck capacity of this path, which is the edge which restricts your flow in this path. In this case, it is 5 because 5 is the smallest amount of flow that we can send through any edge in this path. Send an amount of flow through the path equal to the bottleneck capacity. For each edge in the path, we then create back edges. The capacity of a back edge is equal to the flow sent through that edge. In this case, the capacity of all these back edges is 5. Let's choose the top path this time. The bottleneck capacity here is 4 because this second edge can only carry 4 more units of flow. So let's push 4 units of flow through this path. Now we insert the back edges with capacities equal to the flows of the edges. The back edge on the second edge of the path needs to have its capacity updated to 9 because the flow through this edge is 9 now. The first edge has a back edge of capacity 4. Now let's choose this bottom path. The bottleneck is 4, caused by the first edge. Let's send through 4 units of flow and create the back edges. There is one more path. We can go through one of the back edges. The bottleneck of this path is 3, so let's push 3 units of flow through. Remember, when we push 3 units through the back edge, we take away 3 units of flow from the forward edge. Now backtrack and update the back edge capacities to match the new flows. The first back edge needs to have its capacity updated to 7. This back edge has capacity 3. This back edge has capacity 2 now after we updated the flow on the forward edge, and capacity 7. There are no more paths from S to T, so let's return this final flow as the maximum flow. The flow is the sum of the flows on the edges leaving the source or the sum of the flow values entering the sink. That is 9 plus 7, which is 16. Time to code. The algorithm we will be coding is the Edmonds-Karp implementation of Ford-Fulkerson. Well, you might be thinking, well, where did this come from? So Ford-Fulkerson simply says to find the augmenting paths, but it doesn't specify how. So if you actually want to code it, you need a way to actually find the paths. Edmonds-Karp simply says, let's use a BFS to find the augmenting paths, BFS being a breadth first search. This has the major advantage that in each iteration, a BFS will find the path with the least number of edges. This leaves the time complexity as big O of m squared n, where m is the number of edges and n is the number of vertices. I won't go into detail about this because this video is getting pretty long, but if you guys want maybe another network flow video with proofs about the topics in this video, say a Ford-Fulkerson proof, max flow min-cut, and so on, I'd be happy to do that. Firstly, in my function I'm passing in the flow graph. It maps each node to a list of neighbors. Each element of the neighbors vector contains a pair with the name of the neighbor and the capacity of that edge to the neighbor. Firstly, let's store a mapping of each edge to the current flow in that edge and the capacity of that edge. I also keep track of my back edges in a separate list. Next, let's map each node to a set of its neighbors. We need to go through and create the edge node maps, so let's loop through each node in the input graph. And let's loop through each neighbor for the current node. Firstly, we can insert this neighbor into the neighbors set for the current node. Next, we need to add the edge, so I name the edge node1-neighbor. The current flow of this edge is 0, and the capacity of this edge was given in the input graph, so let's set these. Now it's time to find the max flow. The new flow from an augmenting path is given by BFS. While there is still flow from the augmenting paths, i.e. the new flow is not zero, we want to keep incrementing the max flow by this new flow value from the augmenting path. Then return the max flow at the end. So here we go, let's implement the breadth first search. I'm passing in the node and edge maps. Firstly, we need to map each node to its parent in the path. This is so that when we find the path using the BFS, we can actually go back through the path and update the flows. Next, we keep track of the visited nodes. This is a standard BFS stuff, so we don't keep pushing the same node to the queue and end up in an infinite loop. Speaking of the queue, here it is. So we'll start with the source. And also, I forgot to insert the source into the visited set, but I think that's just being extra anyway. The completed flag denotes the BFS found a path. I start it as false and flip it to true when it finds the sink. Grab the node at the start of the queue. If the node is the sink, we can break and set completed to true. Otherwise, let's loop through the neighbors of the current node. If the current neighbor is in the visited set, meaning it is already in the queue or being processed already, let's leave it. We don't want to add it to the queue again. Otherwise, we would check out the edge from the current node to this neighbor. We check if the current flow at index 0 is below the capacity at index 1 for this edge. And we search for the edge in the edges and back edges lists. If it has room for more flow to be pushed through it, i.e. the current flow is less than capacity, we add this neighbor to the queue and set the parent of it to be the current node so we can backtrack. Then remember to denote it as visited. We don't want to put it in the queue twice. If no path was found, return 0 because we added 0 new flow. This will terminate the entire algorithm back in the Edmonds-Karp function. Otherwise, we need to find the bottleneck of the path. So we start at the sink and go backwards by visiting the parents. In each iteration, check the edge from the parent to the current node, i.e. parent-current node. Then the bottleneck is the minimum of the current bottleneck and the remaining flow which can be pushed through this edge, i.e. capacity minus current flow. For example, if the current bottleneck is 5, but this edge can only have 3 units of flow pushed through it, the new bottleneck is 3. Do the same, but checking if the edge between the parent and the current node lives in the back edges map, because remember I've split up my edges into 2 maps, so you need to check both maps to find the edge. Then move up to the parent of this node. Now we have the bottleneck, we need to correct the flows, and you will see why I split up my edges and back edges. So we do the same thing, start at the sink and make our way to the source. This time we are going to add back edges. These go the opposite way, i.e. from the current node to the parent, so current-parent. If the edge from the parent to the current node was a forward edge, we simply push an amount of flow on this edge equal to the bottleneck. Then we create a back edge the other way with capacity equal to the flow of the forward edge. Otherwise, if the edge from the parent to the current node was a back edge, i.e. we traveled through a back edge in our path, we actually deduct the bottleneck amount of flow from the corresponding forward edge. Remember, the forward edge goes the other way to this back edge we took. Then we update this back edge to have a capacity equal to the new flow of the corresponding forward edge. Because we inserted a back edge from the current node to the parent, we need to insert the parent as a neighbor of the current node. Then move up to the parent. Return the bottleneck flow because that is the amount of flow pushed through the augmenting path in this iteration of BFS. I added a heap of print statements to this, and then I ran this on the graphs in the video and I can show you the paths it took. Here is the first graph. You can see it first picks the bottom path and pushes a flow of 2 through it. Then it picks the top path and pushes a flow of 1 through it. There are no more paths, so it returns the max flow as 2 plus 1, which is 3. Here is the larger graph. It first picks that top path and pushes a flow of 9 through it. Then it picks this middle path and pushes a flow of 3 through it. Then it picks the bottom path and pushes a flow of 4 through it. There are no more paths, so it returns the max flow as 16. It hasn't shown itself taking a back edge yet, but that's because Edmonds-Karp will take the path with the least number of edges because it uses a BFS. And the path with the least number of edges in these 2 examples just didn't include back edges. So I ran it on this new graph. It pushes 4 units of flow through this middle path. Then it gets stuck, so it has to take this path with the back edge. It pushes 3 units of flow through here. And remember, when it pushes 3 units of flow through the back edge, it minuses 3 units of flow from the corresponding forward edge to keep flow conserved. So the flow in this forward edge goes down to 1. Then it returns the max flow as 7. Now you are a bit of a flow pro, you could apply your skills. I made a video about an application of max flow to proving whether a sports team is eliminated based on a leaderboard. So I added this code to the graphs shown in that video too. I'll put a link to all this code in the description.